everybody, and welcome to today's webinar presentation, Never Shard Another Database, Gain Effortless Scale, brought to you by Cockroach Labs. Before we get started, I have a few housekeeping items that I need to go over. First, if you have any questions for our presenters today, post those into the questions panel so we can get to them after the presentation. Secondly, if you experience any technical difficulties today, please post a message into the chat panel and I will work with you to resolve those issues. Last on my housekeeping list, today's presentation is being recorded. It will be available shortly after the webinar ends. Now that we're through those housekeeping items, I would like to introduce you to our presenters. First, Jim Walker. Jim is a recovering developer turned product marketer and has spent his career in emerging tech. He believes product marketing is a strategic go-to-market function in growth companies and helps organizations translate complex concepts into a compelling and effective core narrative and market strategy. The list of startups he has had full-time roles in include ServeGate, Vontu, Initiate Systems, Talend, Hortonworks, Everstring, CoreOS, and his current gig, Cockroach Labs. I know we already heard from Jim, but let's do another quick sound check for him to make sure you're able to hear him, and let me know if you can hear him by posting a message into the chat panel.
Hi, everybody. I'm here.
Perfect.
Great.
Thanks, Jim. And then our second presenter today is Chris Casano. Chris is a solution engineer at Cockroach Labs. His passion resides in assisting customers on use cases, technical adoption, and success with CockroachDB. He has implemented and assisted customers with data solutions in multiple industries over 20 years. Prior to Cockroach Labs, he ran the Northeast Solution Engineering team at Hortonworks, also known as Cloudera. I'd like to do a quick sound check for Chris now. So Chris, please say hello to our audience, and audience, let me know if you can hear him by posting a message into the chat panel.
Hello world, welcome.
Perfect, sounds great. And now I'd like to pass it off to the two of you for the presentation.
Great, thank you very much. I should have just given you an ack, Chris, on that one. You gave me a hello world for your I like it, I dig it. So that, and also, you know, I know there was the Cloudera thing with the Hortonworks, but I guess I was there before it was ever Cloudera, so it always makes me kind of funny. But welcome, Chris. How are you today?
Doing great, Jim. How about yourself?
I'm doing very well. So I'm excited about this topic that we're going to go through today, everybody. You know, this is a webinar that's kind of near and dear to our hearts. You know, we're going to make this as interactive as possible. You know, as noted, if y'all have questions or you want us to cover something, please do, you know, interrupt us and place it into the chat or dump it into the questions. We are more than happy to take questions along the way. In fact, I prefer it. And so if there's really anything that you need more information on in terms of what we're talking about here in CockroachDB or elsewhere, you know, please do ask us questions out. I'll try to get them into Chris as they flow into the overall presentation. You know, but we'll actually leave time at the end for QA as well. And if we haven't gotten to anything, then we'll make sure to address it at that point as well. So, but before I get started, you know, thank you for joining us. You know, good morning, good afternoon, good evening, wherever you are. I say that at every time I do a webinar, but you know, I think it's more important now than ever taking time out of your day to join us. So what we're going to talk about today is the concept of sharding and, you know, what we do in Cockroach database that actually allows you to just not even think about sharding ever again, which I think is actually a pretty interesting concept, because if you've ever sharded a database, yeah, it's not fun. I don't think. You know, I think it's just kind of, it's a necessary evil. You know, the whole concept of sharding really arose because, well, basically we had to scale databases. We had to go beyond, you know, the compute that was a single machine and scale a database out so we can actually get better performance out of that thing. And so this process of sharding really kind of arose over the past, you know, couple decades to really address those needs. And really it is the traditional way of the way that we actually scale out a database. And the process is pretty simple. You know, you take a relational store. You choose a column. You use that as your shard key. You apply a hash across that, which is just very simply a way of shortening that data so that it's kind of easier to access. I think is the easiest way for me to describe what a hash function is. And then you create shards. You basically map values from the big table into different kind of instances of the same table, if you will. And so it's really kind of an easy way of basically saying, great, I'm going to take this table and I'm going to segment it into different pieces, and I'm still going to have an index so I can actually identify that table, but I have kind of basically a representation of the table into two different pieces now, right? Two different shards, if you will. And ultimately, that data gets basically placed into different physical locations. Often we'll see things like, okay, I want to actually shard by price. So, all of the products that I have in my table that are under $50 are in one part of the table. All of the products that are between, $50 to $100 another, and you could really shard on anything. And it's really kind of value-based within the table. Here's a simple table of product and price. And so now I can take, okay, great, all of the values that are in, this sub 50 group, they're living on one server. There's lots of problems with this though. Really, what we end up happening is it causes issues for both developers and for operations. From a developer point of view, when I query a sharded database, I kind of have to know which connection string to use to actually access that data. So you end up actually sometimes you end up dealing with this kind of complicated, sharding logic in the SQL itself, and that can lead to errors or unfound records, lots of different issues, and there's lots of best practices that have to happen over there. What happens on schema modification if I'm a developer and I actually want to start changing things? What does that do for the shards and kind of this very complex configuration of the database? It actually limits creativity and kind of where developers can go. Now, look, I think there's ways to get past that, and I think there's ways to actually automate sharding logic, and I think a lot of people do that. But it is a best practice. But what happens when I want to actually add another shard though? From that point of view, I've got to make actually application changes, logic changes in my code, right? And that's actually, it introduces even more risk. It's really a problem for operations though, sharding. When I do want to reshard a database, that process is not simple. This is typically something that's done in the middle of the night. That's not fun. You kind of have to bring the system down and bring it back up. And if one of these shards or one of these servers fails, what happens to the resiliency of the rest of the application? How do I actually provide these complex active passive schemas based on shards now? It just adds huge amounts of complexity. Think about how we do backups across multiple different shards. What is the backup of a table? And as I was noting, this whole failover bit and what that adds to this whole world is just a nightmare. Ultimately, sharding is possible. It's powerful. It allows us to gain some horizontal scale, but it actually it introduces some fairly large complications and some significant pain. If anybody on the call has never been through the sharding process, I commend you. Thank you. Be happy. But if you have, I think you understand what some of this pain is. I think I get a lot of head nods whenever we go through kind of the pain of what sharding is. And so, sharding came about because, well, in relational data stores, it was difficult to get this kind of horizontal scale. We had to basically scale up the size of the machine that the database ran on, and that's how big we can go, the storage and the compute that was on that physical machine. And sharding really came about. Now, over the years, this concept of NoSQL came about, which actually allowed us to really kind of automate this scale part of things. But what happened with NoSQL is they took the guardrails off of relational databases so they can actually get this kind of scale, right, to automate, read access to data. And what was missing is this kind of transactional capability. How do we still guarantee transactions as we're going to have in its traditional relational stores like Postgres and MySQL and Oracle for that matter? Wow, what a great database, And how do I get those transactional guarantees that are global? Not going through a single write node. And so what's happened over the past couple of years is how do we take the best of the relational world and keep those guardrails on and mix that with kind of the beautiful scale out of things like Cassandra and everything else. and add transactions and guarantee, consistency and allow people to access and write data all over the planet. And that's the emergence of distributed SQL. How do we do all these things and be kind of, architected for cloud and cloud native? And that really brought on the advent of a kind of a new category of database, distributed SQL. I think this thing's been called new SQL, some people called it. I find that to be a weird name. I mean, what happens in 5 years when these things aren't new anymore, right? And I think this concept of distributed SQL is really what's emerging in kind of this new generation of database, right? And so Cockroach Database is absolutely one of these new, kind of cloud native distributed SQL databases. And we are cloud native. We are architected from the ground up to deliver, effortless and elastic scale, to be resilient. These are kind of core primitives of cloud native technologies, yet all the while deliver a very similar, developer-friendly, familiar SQL interface, because I think that's what you want to code. That's how you want to interact with data. We are wire compatible with Postgres, so it works with all the drivers and all the tools that you're going to use with the Postgres. And then we have great syntax coverage across, the SQL syntax coverage as well. There's one thing that we do in Cockroach is a little bit different than anybody else in the distributed SQL world, and that's delivering kind of local latencies at global scale. We can do something in our database, something called Geo Partitioning. The way we partition data, the way that we scale data in Cockroach, and I'm going to explain how that works in more detail, is unique. But we can do things like start to tie data to a particular location. You could imagine the same way we were talking about shards, let the logic of the database deal with where data needs to live, not like the shard key and everything else. Let's let each table define that, users data that was created in Germany needs to stay in Germany so that you can meet things like GDPR. More importantly, user data where people are actually roaming around in, say, South America or in America lives on those servers, so that I have low latency access to that. And Geopartitioning is kind of a unique feature that we do that allows people to actually go forth and do that. And so, this is kind of a new category. And Cockroach really was architected as this. And this is tech that was originated at Google. There's actually a database as a kind of precursor to ours, and it's Google Spanner. In fact, the Spanner white paper is where we got a lot of our kind of interest in this. But we've been building for 5 years, and this is a unique architecture. If you're familiar with things like Cassandra, it's kind of like Cassandra, but have a really powerful Postgres type experience on top for transactions and language, right? And so you can kind of scale Cockroach fairly easily. You spin up a node anywhere, you point it at a cluster, and underneath the covers, Cockroach takes care of redistributing data. Cockroach takes care of, when I lose a node, repairing that and making sure that I have copies of that data. It's going to coordinate transactions so that when somebody accesses or writes data in New York and somebody writes data in Singapore, two conflicting transactions, who wins, right? And so it provides kind of a lot of magic underneath, but I'm going to let the product actually show this more than me just talking through it. This is kind of a baseline. So Chris, are you still with me out here?
Yeah, can you hear me?
Yes, I can, buddy. So what I'm going to do is I'm going to toss over controls to Chris, and we are going to let Chris now show everybody some of these concepts in action in Cockroach Database.
Cool.
I didn't know our cameras were on, buddy. Hi everybody. I hope I didn't do anything bad. Was I scratching my head or looking the other way? I didn't oh boy.
You look beautiful, Jim. You look beautiful.
You never know these days, right? So thanks, buddy.
You might have to pass me control.
All right, change presenter to Chris Cassano. Okay, buddy, you got it.
All right, how am I looking?
I can see you loud and clear, buddy. It's great.
Awesome. All right, so I'm going to take you through a quick resilience demo. I'll show you how Cockroach works. If you want to see this for yourself, there's actually a great tutorial we have in our documentation. If you go and search for docs, it's right here. There's a tutorial called Fault Tolerance and Recovery. All I did was script out this tutorial, and we can even put it in the chat too if people want to pick it up from there. Let me put that in the chat for everyone. All right, there you go. So what I'm going to do is I'm going to run this demo. You're going to see, and I apologize, a lot of database demos are from command line, it's just how it runs, but there will be slides that will show. But yeah,
I like
so
CLI.
Sorry, Jim?
I like the CLI.
All right, yeah, we'll kick it old school. So what we're going to see in a demo is I'm going to bring up an environment. You can see a Cockroach cluster that's going to be stood up. We're going to have 6 nodes in the cluster. I'm going to show you how the data is distributed through the cluster, and then I'm going to take you through a set of resilience demos that you can see. By resilience, what that means is that we actually have, like I said, 6 nodes that are live in the cluster. We'll actually remove some of these nodes so you can see that the database can continue to transact. And then if we even want more resiliency in the database, we can increase the replication factor of our data so that we can incur even more failures. So I'll take you through how this works. But first, let's get out of the command line and I'll take you through the admin UI real quick. Hopefully this looks okay. Let me just make it a little bit bigger so everyone can see it. This is our admin UI. And you can see here I have, let me just refresh one more time. You can see here I actually have a workload happening. So I have, a couple of SQL transactions happening, a couple of reads and writes that are happening in the background. And if we look at the database itself, we can see we have 6 live nodes. We have 6 nodes. This is all running locally on my machine. But as Jim mentioned, we're cloud native. You can run this in Kubernetes. You can run this on VMs in the cloud, bare metal. We're infrastructure agnostic. And what we're going to do now is we're actually going to go remove, actually before I even remove one of the nodes, let me just show you the database that we have set up. So I have a benchmarking database called YCSB. It has a single table that's in that database. And since this is all about sharding, this talk, let me show you how the shards work. So in the cluster, we have, like I said, our database YCSB and a user table. We can see that table is actually broken up into three replicas across the cluster. So we have a replica on node 3, a replica on 5, and a replica on 6. And as the tables increase, we can create more ranges that are scattered throughout the database to give us all that resiliency. And like Jim mentioned, this does all the sharding for you. You don't have to think about shards at all. We do it all underneath the covers. And anytime you connect to the database, you don't have to think about what node to connect to. You can connect to any node and access the data just like you were if you're on a different node. And let me show you. So this workload is running. Let's go into the database real quick. Actually, I might have this. Yeah, here we go. 26257. All right. So right now I'm on. Let's see what node I'm on. So I'm actually on node 1, right? And we know from the diagram that you see here that there's no shards on node 1. It doesn't matter though, because we can actually go and select the data from that table, because Cockroach knows underneath how to communicate between all the nodes and report back the information. So regardless of what node you're on, the entire database, any node on the database serves as a gateway as to where you can get data. Okay.
So Chris, basically what you're saying is there's no single write node, right? Everything can read and write, right? And it just finds the database throughout the entire cluster.
Yep. And right now I'm only running on my laptop, but I can have a database that spans multiple regions all across the world. It's one instance that spans everything. And like I said, each node is a gateway. So if I can enter the node in New York, I can query data all the way in China, for example. It's rather unique. Okay, so now that everyone understands the concept of what's happening here, let's go back to my my main screen here. We can see that we have 6 live nodes. What I'm actually going to do is I'm going to remove one of those nodes. So you can see my script here is stopping one of the nodes. We'll come back to the UI, and you'll see here in just a second that the database is going to recognize, hey, something's wrong. One of my nodes are down. I'm going to let the user know that I have a situation. So you can see that I have a suspect node, and the database is very patient. It realizes, hey, something's wrong. Let's see where this goes. Let's see if this node comes back to life. If not, I'll start replicating the data so that I can, maintain resiliency. And you can see too, like the transactions continue. The metrics are showing that we still have things happening on the database, even when there's interruptions like a node failure. what I can do is
Hey,
I can bring
Chris,
that up.
why does it say suspect node and doesn't say failed node, right? Because that node is gone, right?
Great question, Jim. Yeah, so like I said, the database is patient. So it realizes the node is something's wrong. It puts it in a suspect state. After a certain amount of time, by default, I think it was about 5 minutes, we'll actually remove that node to be in a dead status, where, hey, this node is no longer part of the cluster. We have to continue on, and that's when we'll start repairing. We'll start doing the replication of the data in other nodes to make sure that we have a balanced set of replicas all across the cluster. Okay. I just brought that node back to life. So, you know, it connected back to the cluster. It checks with the other replicas to make sure that it's, you know, that it's up to date and then in sync. And off we go. Cluster's happy again. All things are great. Now, the default replication factor that Cockroach comes with is a replication factor of 3. But you can increase that. You can create it to be 5 or 7 or 9. And you typically will do that to create more resilience or to have your data replicated in multiple places for really, you know, heavy read type of operations. But in this case, I want to show you an example where I can actually change the replication factor on the fly. I'm actually going to increase that replication factor up to 5. And this is a live, you know, live system. And I can say, hey, go create more replicas. And you can see here on the status is telling me that I have, you know, some of the shards that are under replicated because it's doing a background process as far as creating more replicas. And then, you know, in just a second or so, everything will be replicated more. So why am I doing this? Well, I want to show you that I can incur even more node failures now. Because I have a replication factor of 5, I can take 2 nodes out of the cluster without having any impact. So let's see that. So now I'll remove 2 nodes. And you'll see here, I'll have 2 suspect nodes. And again, the database will continue to transact. Actually, my workload might have ran out of time. Yeah. So my workload ran out of time. I only had it set for 5 minutes, and then that means I'm talking too much. But what's happening again is that, you know, 2 nodes go down, database continues to transact, and all is well. So that just gives you an idea of how resilience works within Cockroach and how we, you know, set up the data so that it's sharded all across the cluster. So you don't have to go thinking about shard keys, where data is located, how do I connect to which shard. It makes, you know, the application developers experience really simple and easy, and the operators as well, because now I only have to manage one cluster. I only have to manage one backup. I don't have to work about, you know, backups on all these different sharded databases like I would with the legacy system. You know, the idea behind Cockroach is to make data easy, and that's what our database does.
Right. So Chris, you talked about a couple things. There's like range and replication. So range is like a shard, right?
Exactly. Yeah.
And I'll go through that in a second of actually how we actually build out ranges, and we'll show that in some slides. But you were talking about replication as well. And so what is replication relative to ranges? Because you went through it a little fast. Like we changed the replication factor from 3 to 5. What does that mean in terms of like the tables and what's being stored?
Yeah, so great question. So anytime you have a table or an object in the database or an index, what we do is we create shards for that particular object. So let's just take a table, for example. For that YCSB table that I showed, we created, you know, a shard for it. Let me actually show you. Yeah, if we want to take a deeper look at that table, of that user table that I mentioned before, you can see that, you know, we increased the replication factor of 5, so we can see each of those replicas are across nodes 2, 3, 4, 5, and 6. So node 1 is the only one that doesn't have a replica. And additionally, with that particular replica set, one of those are going to be elected to be the leader of that group. So in this case, that leader is on node number 2, and that range or that shard is going to be responsible for all the reads and writes for that particular range. Now, if my table got bigger, I would actually see more entries here. And I would see the start key and end key for that table, and how that gets broken up for all the different shards.
Right. And so the range basically is just a segment of the table. It could be all records from Cassano to Duckworth or something, right? And like those records get written multiple times throughout the cluster.
Correct.
That's right.
Spot on, Jim.
Okay.
You know, that's pretty good.
Well, hey, you know, I am a marketing guy, so I got to figure out some of these things. So let's. let me show you all how this works underneath. Now we can actually show you in the product kind of what's going on, but let me show you exactly kind of the architecture of what we built. And actually, ultimately, this looks like a relational database, but at the storage layer, we're actually using KV to accomplish a lot of this stuff. And this is really where the magic of Cockroach database comes through. So let me get this window back up. Let me get here, webinar, where are we? Good. Great, can you see my screen again, Chris?
Yeah, it looks good.
Great. So every table in Cockroach database is really represented as this monolithic kind of KV store. So here we have a table. This could be the dogs table, and I have, 12 records in it. These are all names of dogs, right? Carl and Downey and Figment and Jack, right? And what we do is we order them. We order them lexicographically by key. So the K in the KV store is one big ordered set of information, right? Now, this is different than a regular database. Like back in the world of a regular database, our table, our inventory table, we would just keep adding rows to the end of this. And if we wanted some sort of order to this, well, we had to actually create kind of a new table, an index, if you will, in the structured data model that actually mapped and pointed to the records so that they always stayed in order. And that way, when we wanted to enter a new record, we just append here. And we had to change the index to actually understand where things were in terms of the ordered pairs or how the table was ordered, right? And so that's kind of how this used to work. Well, with us, it's very different. We're actually using KV to do all of this, right? We're actually compiling a lot of this capability into one thing. Now, by having a KV, we get some really kind of core, powerful values in terms of how we access that data and what we can actually do with it. But ultimately, at the bottom of what Cockroach does is KV. Now, the critical part when you're thinking about implementing Cockroach database is really thinking through the K, the key in the key value store, because that is really what's going to set that kind of this tabular data in motion. And what we actually compile into that key, it's all encoded in bits and whatnot underneath, is really going to be the power of what we can actually do when we start to split data up, because we're going to split data just like you had shards in a table. Maybe I took one table, split it in half, and had two shards. Well, basically our ranges, our shards are actually going to be 64 megabit chunks of data. So is it every 4 records? Is it every 10 records? And then that data is going to be replicated across the cluster. Let me show you how that works, right? So in a relational world, we have a table here where it's over on the right. There's our dogs. We have an ID, name, weight, right? That says simple, how we create this table. It's a hex of our, a string basically and a float, right? Well, when we actually store this data underneath, we're doing something very different. We're taking each of these rows and we're going to translate it to KV. And we do so by taking each row and saying, look at, for every column in this row, we're actually going to store the value relative to the key. So I have, this table is called dog, the ID, the primary key is 34. And for the column name, I'm going to write the value Carl. And for, the table dog and the primary key of 34, and the weight column, I'm going to write 10.1. So that actual row got written as 2 different values. Now, what I'm able to do is actually go down here, and now I have this huge table, but it's all written as KV, and I'm able to sort now by the key, and I can completely sort the entire table now by key, and I know exactly where I'm at in this table. Now this gives us some really interesting power, because what we actually encode into the key becomes critical in how the database is implemented. Now we can actually change primary keys on the fly, so all these things get moved around. Everything else, it's another story, but we can actually do some really cool things on there. But that, at the core of what we're doing, right, in Cockroach database, and what allows us to actually do something very different is here. And it's this monolithic ordered key value store, which allows us to do some really cool things, right? We can have these huge efficiencies when we start sorting through value. It ensures us against null values. You can't have a null, right? And then it allows us to maintain integrity. So we're going to take this monolithic logical key space, and we're going to now put this into the database. And this is going to show how we actually shard the data underneath, right? Our key space is going to be divided into these contiguous 64 megabit ranges. And so this is kind of like I was talking about. These are what we think of as shards. So here's 3 shards. The database actually understands the size of each one of these shards, right? It says, look at, here's my table. Let's cut it all down into these 64 megs. So in this case, I had 3. So, but we also need an index so that we can actually find this data. So in the application, you know, it's ultimately implemented very much like a B tree, if you're familiar with that. It allows us to do some really cool things in that context. But we also get like range scans. We can do this now because we know which ranges things are in, and we could find, you know, say all dogs that are between Muddy and Stella. We only have to actually go through 2 of the shards, 2 of the ranges, and we get all of that because we actually understand from the KV point the order of the data that's in these shards, right? Which is actually, we can do a lot now in that K. It's not just the primary key of the table. We can actually encode lots of things into that, right? So what happens when we want to insert data? I want to insert a record, Sunny, into this table, into the dogs table, right? Well, I'm going to go through the index. I'm going to find out where that is, and it's in the 3rd range here, this red one, right? And it's going to fit in here somewhere between, you know, Stella and Z, right? Do I have enough room? Yes, great. Okay, great. I'm going to insert that record. What happens when I want to insert another record into that range or into that shard? Well, what it's going to do is going to say, hey, look, I don't have enough space right now, so you're going to have to actually split this range or this shard into 2 and then insert the record. So what I've done is I've just actually resharded the database, y'all. But the database is actually taking care of all of this. Underneath, automatically, it's actually taking care of saying, like, I don't have enough room, so create a new shard, if you will. It's just a new range for us. Add a new row into the index, and then now I'm able to actually find that data, right? So I split the range, I insert. We actually aren't doing this in real time. We'll allow ranges to go a little bit bigger than 64 megabits, and then at a time when you aren't accessing that data, we'll actually do some cleanup and make sure everything's cool, so it doesn't hold back a transaction while I'm doing the splitting process, right? And so that's actually what's happening underneath the covers. Now, Cockroach Database is taking care of all of this. All you do is configure the database, and as tables grow, it is automatically changing and resharding that database underneath, if you will, and just basically creating new ranges all automatically. So how do we place these replicas in a cluster? So Chris also mentioned how we're able to survive failure of nodes and failure of you know, when a shard goes away, what happens? Like I still need to actually be able to access that data. Well, there's different ways in which we can actually survive data. We can survive, you know, a disk failure, a single machine, a rack, a data center, a region, right? And what we do is we actually kind of store data in ways that will allow us to do that. In this case, we want to actually, you know, survive, say, a failure of a node of Cockroach Database. Well, each range, each shard is written 3 times across different nodes in Cockroach Database. And that's how we actually, our name is, we're very resilient, right? Now you actually configure this at the table level and you tell it exactly how you actually want to do these things. We can actually reconfigure things on the fly. But in this case, I'm going to have my replica factor is set to 3. So Chris talked about that. So what the replica factor was saying is like, take this range and write it 3 times. And that's what we're doing. So we took the first range, we wrote it 3 times across 3 different nodes. We take the second range, write it 3 times across 3 different nodes, and then we take the third range and write it. And what we've done is we've kind of even balanced this out, and it's for diversity so that we can actually survive the failure of a particular node. Now, if these nodes lived in different regions, you can actually configure the database to say, hey, look, I want 1 copy of the data in 3 regions or in 2 regions or whatever that is you want to actually specialize. But that's done really just via a simple alter table command in the database itself. The database underneath is actually going to take that command and deal with how it's actually distributing this data, right? So what happens when, you know, another way we can actually place data in a cluster? Here's a 6-node cluster. Sometimes a particular range or a shard of data is being used more than others, and we'll want to actually just place that into its own compute so that we can actually deal with that high load. And so the database is actually collecting heuristics and can move data around based on utilization of the particular node itself as well. So in this case, we're going to actually segment out this blue range or this blue shard. We're going to move data around so that it's actually segmented off on its own nodes so that it isn't competing for you know, resource contention in particular nodes. And we can now optimize the compute side of things as well, which is kind of interesting, kind of unique, right? Again, all done by the database underneath, no manual sharding, no, you know, dealing with this stuff. So what happens when we add a node, right? I think Chris did this, right? So when we add a node to the cluster, the database is smart enough to say, hey, look, I've got some more resource over here. Why don't you rebalance things? So in this case, it's going to take that yellow or orange range, and it's going to move that to the node and clean up on the old node. So again, we have this balanced resource utilization. So I've just simply scaled the database by spinning up a node, pointing it at the cluster, and the database is going to rebalance everything for us, right? And so we did this without, a simple spin up of a node and pointing it at the cluster, simple configuration. Well, things also fail. Chris showed this. We bought down a node. Well, there's 2 replicas that are missing. I can still access the data because I have copies of that data all over the place, right? I have orange here, I have blue, and I have red. Okay, great. I have my complete table, but you know what? This under replicated data, that's what Chris was showing in the UI. That's represented by these 2 ranges are gone. They were under replicated ranges because that node has gone down. And so what happens is the database basically just it eventually over time, it will realize that that node's not coming back and create new replicas of that data, because each range, each part of the table, each shard knows that its replication factor is 3. So it says I have to have 3 copies at all time in this cluster. If I went to 5, I have to have 5 copies at all times in this cluster. This is how we provide this kind of very bulletproof resilience, right? A node can go down, I still have access to the data, but I've also made sure that I still have replicas across the entire cluster, which is extremely powerful. And again, all of this is just happening. The database is just doing this underneath. We can also, survive a temporary failure. If and a node doesn't always just go away. Sometimes a connection is janky. And so it can replay things as well. So we don't have to actually remove data every time something goes away, like every second. We can actually give it a little bit of time maybe to actually deal with that as well. We can also do something very cool and very unique to Cockroach. And if we were able to, in each of the keys of the table, actually overlay a location. Let's just say we take the country code for each one of these things, or maybe a location we want things in. We put that into the primary key. Well, the database is smart enough to understand by primary key, do something called Geopartitioning. We could take data and if these servers actually have a name attached to them, we can actually tie data to a location. So look at all the blue data is going to live in US East. All the red data is going to live in US. Oh, wow, I have to change the slides. Do you see that? This should be red down here, y'all. So all the red data is going to live in servers in US West. And we do this because, well, sometimes you need to increase or optimize latency of access. So, maybe this is the West Coast users are all on West Coast servers. A lot of times people use this for GDPR and data privacy regulations. How do we make sure that data is just accessible in certain parts of the world or tie it to particular servers, right? And so this is just another way in which we can actually place data within a cluster. And it comes back to this KV store underneath. Meanwhile, this is just SQL to the application. This is just SQL to the developer. This is just familiar Postgres that you know and love, but underneath the covers, it's doing all this magic using this kind of this core capability of what we're doing at the storage layer, right? So Cockroach ultimately allows your data to be always on, always available. We're going to survive a failure. This eliminates the need for this kind of this costly active passive systems, right? Because everything's active, everything's on all the time. One of the really cool things that Cockroach also allows for, if you think about this, it allows for rolling upgrades. We do allow for schema changes too. We can bring down parts of the database and bring it back up and everything's fine, right? And we can mitigate schema changes. More importantly, we can have multiple versions of the database all running in the same cluster, and we can bring down one node at a time to upgrade an entire database. If anybody's ever upgraded a database, typically this is one of those things you do at Sunday morning at 3:30 in the morning when you have your lowest traffic and you're just trying to basically mitigate the risk of the downtime. But we can actually roll out and upgrade a database in real time in production and just bring down node by node and spin them back up with the new version of the software. So it's kind of one of these unique capabilities of this resiliency capability. So I'm going to go back to you, Chris, to actually demo that. And what did I miss? Did I miss anything here? Or is anything you want to expand on?
That's precisely what I'm going to show. The way we built up, the way we built up Cockroach was to always be, like Jim mentioned, always be resilient. So things that would typically take downtime with databases, like rolling upgrades, like backups, like garbage collection, all those are not, we've made the database so easy that you don't have to worry about those things. The database is always online. You could do online schema changes. You could do backups. You could do rolling upgrades. I'm going to show you that as part of the demo just now. Okay, so again, can you see my screen okay?
Yes, I can, Chris. Sorry, I was on mute, buddy.
Okay,
Hey,
cool.
can you see my screen? I feel like, can you see my screen? Like those words I have been said more in the last 3 months than the history of the planet.
Can you hear me now?
Can you see my screen? Can you see my screen?
All right, cool. So here's what we're gonna do. I just spun up another 5-node cluster, and you're probably saying, "Hey, this looks different. Why is this, UI different from what you showed me before?" Well, I'm actually showing you our old UI because we're gonna upgrade to the new UI or the new version of Cockroach. So you can see here that we're on the 19.2.5 version. Each one of the nodes here of the 5 nodes are on that version. We see the cluster's healthy. We have 5 live nodes. We have nothing under-replicated. And we're also running a workload, right? So kind of the same workload that we had before, about 50 transactions per second or so. And we're going to go through an upgrade. So what the upgrade does, I just have this scripted out, is that we're going to go through each node at a time. We'll bring down a particular node, swap out the binary, and then bring that node back up into the cluster. That's it. So the script will slowly go through this, and you'll see the cluster come to life. So let me kick that off. It's going to start with node number 5. So if we go to the UI, you'll see that as this goes through, we'll see that the new version for each of these nodes will change. You can see right now I'm on 20.1 for node number 5. Then I'll do node number 4, node number 3, and so forth until it's done. You can see it's changing here. And all this time, the workload's going, right? The database even knows that we have staggered versions. We have 2 different versions of the database. So again, it's very self-aware and patient as you go through the process. All right, so let's go back over here. Still going. I think we're on the second one now. And we're just about there. We got one more. All right, should be good. I'll do a refresh of the UI, and you'll see that we're now in 20.1, right? We have a completely new UI here. And if we go back and look at the metrics, you can see that the database is continuing to work throughout the process. So yeah, very straightforward, simple rolling upgrade that you can do with the database. Doesn't, you don't have to incur downtime. You just have to make sure you're prepared. Making sure that the cluster's healthy, making sure nothing's under-replicated, and then being very methodical as far as how you go about, bringing down a node, swapping out the binary, and bringing it back up.
That's cool. So Chris, did you is this UI basically, did you upgrade that separately, or how did that work?
Yeah, no,
I saw the UI improve, right?
Yeah, so it's all part of the process. So what's nice about Cockroach is that everything's in one binary. The admin UI, the coordination between the nodes, the client, everything is in one binary. So it makes the usability really simple. So I don't have to, do a separate migration, a separate upgrade for our admin UI versus the cluster and the client. It's all one binary. So it makes it really simple, especially if you're running this on a technology like Kubernetes. You just have one container that you have to manage. It becomes that simple.
Interesting. So one binary, basically, that's another kind of core principle of being cloud native, right? It's one, you're doing different types of nodes, and basically it's not a single point of failure either, right? So if that node you're kind of connected to right now, which is what I guess your local node, went away, you would just connect via to just a different node, and you would have the same UI up and running, right?
Correct. Yeah. So that's you're one step ahead of each other. So what's great is that that admin UI it's not on a separate service. It's just part of the architecture.
Right.
can go and get it on any node. So you can see here, I'm showing you, hey, this is what the node configs are for each of the nodes in the cluster. And if I want to get the admin UI from this node, I can go to this port, on this one, and I can go to this port, and so forth. So even HA within our admin tools are just built right into the database.
That's cool. That's
Very
cool.
fancy. Yeah.
And then Chris, I don't know if you touched on this before, but you showed, I think, a YCSB workload before.
Yep.
I think there's a couple other workloads and everything else. Can you just talk about Cockroach Demo as well? I think that's a really powerful part of what we have.
Oh yeah, I love Cockroach Demo. So yeah, let me show you real quick. So we do have a tool within the binary. Let me clear out this. So if you just want to quickly spin up a cluster, you could just type in Cockroach Demo, and it brings you up a cluster that with some sample data. I can do show database here, and you can see I have a mover database, and there's tables in here, and I'm off and ready to go. I can, for developers, this is fantastic, right? I don't have to really think about setting up a whole infrastructure. All I have to do is type Cockroach Demo. I have a database that's up and going, and off I go. And on top of that too is that with Cockroach Demo, let me just bring up the commands, but we have ways that you can just spin up an entire, a Geo Partition database with Cockroach Demo. I'll show you real quick, and add some load to it. So check this out. So this is actually going to spin up a 9-node cluster on my machine. And let's go to the web UI.
Oh, you missed, there you go.
Yep.
See, you see that I was QAing your copy paste, Chris? Just
so good, such a good teammate. But check this out. This is really cool. I have a 9-node cluster, and it's simulating, having all my nodes in different regions. So I have 3 in the West, 3 in the East, and 3 in Europe West. And there's some load here as well. So I can go here and I can see that it's doing some, selects, updates, and so forth. But I can start getting a feel of how I'd work with a geo-distributed cluster just by using a single command to set up a node to set up an environment to go test with.
That's cool. And so then you can play with this code. You can do whatever you want with it. Yeah.
Yeah. Interact with it just like it's a,
cool.
Interact with it like it's a database.
Awesome. Yeah, and I think the other thing is, I think our documentation is also just really stellar. If anybody is starting with Cockroach Database, downloading it, starting, going to Cockroach Cloud, doing it there, we give you a free version of it too. I just find it to be extremely powerful, especially the docs. People talk to us all the time about how powerful our documentation is. The team does an amazing job. So, but if you want to actually read what Chris and I were talking about today, the reference section and all the architecture and everything else, it's all out here, right? So, cool. All right. Well, Chris, I'm going to wrap it up here.
Okay. I'm gonna pass it back to you.
Okay, everybody. So everything that we just went through. Oh, there we go. The last 2 points I just wanted to make is through all that, we are actually guaranteeing consistency as well. We actually implemented serializable isolation. So this isn't casual consistency. This isn't eventually consistent. This is truly consistent data, so that, like Chris was showing in terms of having a cluster that is geo-distributed across the entire planet, having transactions happen in 2 different spots, how do you actually coordinate that stuff so that you don't have, write skew or dirty reads or other, transactional issues? And so we've taken care of that. We actually, by default, implement serializable isolation, which I think is actually a pretty cool thing. It's one thing to, be distributed. To do that and guarantee data is a wholly other thing. Cockroach is being used for lots of different ways. This is really designed for these kind of heavy read-write distributed transactional workloads. Anywhere you would use a database for an application, that's where we think we fit. If you don't want to shard your instance of Postgres, or you want, an active passive kind of resilient system out of the box, now that people don't think about that when they start an application, well, you don't have to think about that even when you get to that point with Cockroach. And so we're seeing lots of different organizations use us in these different ways. I think it's pretty cool. SpaceX is on here. I think we're in space now, which is cool. So So lots of organizations using us, and you know, I would encourage people to check out our Slack channel as well. Lots of people in these organizations are there. They're communicating, they're sharing best practices and some of their own challenges in their application. And so we'd love for you to get started. You could go use Cockroach Cloud today. If you go out to CockroachDB, get CockroachDB on our website. We'll actually spin up a cluster for you, free for use for 30 days. You get all the capabilities we just saw, or enroll in Cockroach University and get hands-on coursework. Will and Lauren are amazing instructors. That's who's on the screen here, and there's some really great coursework for you to learn more about Cockroach. But with that, thank you. We actually hit all the questions that we had during the session. I was trying to throw them into Chris. So with that, I want to thank everybody for attending. Chris, thank you for joining too, buddy. Thank you for your great demo.
My pleasure. Always fun. Always a great time.
Buddy. Cool. All right, everybody. Thank you and have a great day.
Perfect. Thank you, Jim and Chris, for that phenomenal presentation. And D-Zone would also like to thank Cockroach Labs for providing the audience with a great webinar. Lastly, thank you to everyone who attended today. We hope you learned something new that will help you in your developer career. Have a great day.